Hello. So I'm gonna talk about pulse width modulation. Give me one second. So what is pulse width modulation? Okay. So this is a circuit inside the microcontroller. Let me change the color. Oops. Oops. Okay. Oops. Okay. So if this is a microcontroller, okay, there is a circuit here inside the microcontroller. This circuit, we call it pulse width modulation. This circuit should have pins, external pins. How many pins? As I'm going to explain right now, 8 pins. Okay. So I'm going to give you more details, but for now, I want to tell you something very important. Pulse width modulation, it has no interrupts. I know you may be confused, but because we have been we talked about interrupts for a while, so everything we taught maybe for several weeks was about interrupts, but now pulse width, this one has no interrupts. Okay, so why it is useful? This pulse width modulation. It is useful because you remember when I talked about the timer system, I told you how can we generate a square wave signal. I told you there is interrupt here, there is interrupt here, interrupt here, and interrupt here. And in every interrupt, you remember when I said TCX should equal TCNT plus some value. So you have to execute, so you need interrupt here. Okay, so interrupt means you need some time. You need some time from the CPU, from the microcontroller. Pulse width modulation is completely different. Well, pulse width modulation, all what I need from the microcontroller is just to set the circuit. This is a microprocessor, but microprocessor has to set the circuit here of the pulse width modulation. Once you set the circuit, the circuit is going to generate square wave without. We don't need, after that we don't need any time from the microprocessor. You understand what I'm saying? So the square wave is just going to be generated by the external circuit. So I don't need any time from microprocessor. So here, at least microprocessor is going to put some time here. Here, I don't need this time. That's very interesting. This is the other interesting thing is, and this is very important, is it's very easy, very trivial, very easy to change the duty cycle. Okay, that means you can generate signals like this, something like here, something, for example, like something like that, okay? And very easy, you can make this signal. Sorry. You can make it something like that, very easy, okay? Very easy, you can make it here, something like that. You can change the duty cycle, okay? Sorry. And so on. So it's very easy. You can change the duty cycle, and I'm going to explain why you are seeing this is very interesting. It's very interesting because number one, it's used to run the servo motor. It's also used for something else. I'm going to explain now. Okay. So here, for example, if you have like a bulb, or if you have a van, and I apply a square wave here to the van. I apply like a square wave this way, or to the bulb, to any one of these two. Okay. So actually, the speed of the fan is going to depends on the average. What is the average voltage here? Okay. As we increase the duty cycle, the average voltage should increase. So for example, this one, it has much bigger average voltage than this one. Okay. So as we increase the duty cycle, again, remember what is the duty cycle? Remember the duty cycle was T on divided by T, right? Times 100 to be percentage. Okay, so how big to do the cycle can tell you how big is the high voltage here. Okay, so as we see here, guys, in this graph here, and if you go this way, I'm increasing the duty cycle. You can see here, this one has a small duty cycle, now I'm increasing it. Because I'm increasing the duty cycle, you can see the average voltage is increasing. So if I apply this signal here, okay, so that means this the light in the very beginning, this bulb is dim, okay, and then as we increase the duty cycle, we actually we increase the lighting, the light. Same thing here for the fan. The fan speed is going to depend on the voltage anyway. So that's what I explained. In pulse width modulation, we have 80 channels. Okay, if again, no interrupts. Don't be confused. 80 channel. Every channel should have external pin in port P. Port P. Okay, that means and they are independent. That means you can generate 8 if you need, for sure. You may not need all of them. You can generate up to 8 signals here, different signals. You can do that if you want. Okay, how it works? I'm going to tell you how it works and the main idea here. Number one, we have a clock. I'm going to tell you later where this clock is coming from. But what I'm saying, we have a clock. This number one. Number two, every channel should have 2 registers, as you see here. One is called pulse width modulation period, and one is called pulse width modulation duty cycle. Okay, this pulse width modulation, for example, duty cycle is telling you how big is the high signal here, how big it is. Okay, a number of cycles here. For example, if this is like just a register. If this register I put 50, what it means? It means this one from here to here should equal to 50 cycles. 50 cycles from here. And this one, same thing, the period has to tell you how big is this one from here to here. Is that okay? That means if you put, for example, here 100, that means this from here to here it's 100, this one here 50, and this one for sure should be 50. That's why it should be 50% duty cycle, because it's the high voltage, low voltage have the same time. Okay, so here, and this is what you should understand, I can say this is a pulse width modulation signal. So this signal, actually, I can get it by dividing this signal by 100. Makes sense, right? Why? Because every 100 signal here, we are going to generate only one period here, or one cycle here. So that's why, yes, it is. This is how it is. So you actually, the output signal here we get here is actually the clock divided by 100. It's the number you put here. Is that okay? That's why, that's what I'm saying. That's why it is very trivial to change the duty cycle. How? I can, if I put here 100, if I put here 10, so now I have just a register. We did it many times. You just, this register, you put some value in this register. If you put 10, now I have 10% to do the cycle. If you have 12, if you put here 12, so by this way you can make the signal bigger easily. If you put 90, so now it's 90. So 90% to the cycle. All what you have to do, just to change this register, okay? So now I told you we have a clock, and I told you I'm going to talk about it later. Where is this clock is coming from? So now I'm going to talk about it. So this clock, as you see here, we have the E clock. E clock, as we said many times, it's 24 megahertz. Okay, this E clock, I'm going to divide it by a register, what we call prescale, similar to prescale we used before. So I'm going to divide this frequency by one of these values. This is the prescale, and there is one register. You can select whatever you want here, and then you can divide it by N, and N is another register. Okay, it's called scale to register. Okay, and then you can divide it by 2. By this way, I'm going to get a clock we call scale to clock A. Okay, this one is scale to clock A. So scale to clock A should equal 24 megahertz divided by this prescale divided by this register divided by 2. Okay, and if I get this frequency from here, this is what we call clock A. Okay, so this frequency here is just 24 megahertz divided by prescale. Okay, so now for the channel 0, 1, 4, and 5, you can select the clock from here or to here. You have 2 options. That's why you have a register for configuration to select. Do you want this channel to work on this clock or this clock? Is that okay? So this is for this 4 channel. Okay, what about the other 4 channel, 2 and 3, 6, 7? For these channels, it's exactly the same thing, but we have different. So here, this one is 24 megahertz. So we have a register here, prescale, which is different from this prescale. Also here, this one is different from this one. It's the same, but we program them separately, because the scale here, the prescale is different, and also the the register here also is different. Okay, so now I can say, so if you look here, guys, I can say this clock should equal 24 megahertz divided by prescale. But this clock here should equal 24 megahertz divided by prescale, okay? Divided by this one, pulse width modulation scale register, and then divided by 2, yes, okay? And then this frequency I'm gonna get here is the same clock here. This is the clock I'm gonna use here. So I'm gonna divide this clock again by this one to get the pulse width modulation output clock, okay? So this is the final formula. If you use clock A or clock B, by the way, they're almost the same. Or if you can use scaled A or scaled B, okay, this is the formula. Pulse width modulation frequency should equal 24 megahertz divided by prescale. Remember, this is the clock frequency. And this clock frequency, I'm going to divide it by the period, as I said before, okay? But if you use the clock, scale to clock, so number one, this is the frequency, 24 megahertz divided by prescale, divided by 2, divided by pulse width modulation scale register, okay? And then you divide it again by period, okay? So here, this is the formula we have to use. So this is how can you program the pulse width modulation. It's very trivial, very easy. All what you have to do is just, you have to select some values here for the register so that you can get the frequency you want to get, okay? So now I just want to tell you, is there a limitation? Can I generate any frequency? For sure, no, you cannot generate any frequency. For sure, there is a limitation. Limitation here, I mean minimum and maximum values, okay? So how can you get minimum or maximum values? For example, let's select this one. So here I'm gonna put here minimum, okay, to get the maximum one. Or I put maximum to get the maximum frequency. That's what I did here. So in order to get the maximum frequency, I'm gonna put here 1, which is the minimum. So I'm gonna put 1 and 1. So by this way, the maximum frequency I can get is 24 megahertz. For if you use clock A, the minimum frequency is 732. I cannot get lower than this value. I cannot get more than 24. Okay, and I can get this one by putting the maximum here. So prescale is 128 and the pulse width modulation period is 256. Same thing for scale to clock A, same thing. I'm gonna do the same thing. But here, look here, my maximum is 12 instead of 24. Also, my minimum is only 2 hertz. It's much lower. You know why it's much lower? Because here I divide by 2. It was not here. I divide also by 256. So I divide by more numbers. That's why it's lower. Okay. So how this can be useful? Very easy. Look here, guys. If you want to generate a certain frequency, okay, in order to select, should I use clock A or scale to clock A, you have to make sure this frequency in this range or in this range. You got what I'm saying? For example, if I ask you to generate 13 megahertz, so I have only one option. This one. This is the only option. I cannot use this one. Why? Because the maximum here is 12. So this is very important. So now for each clock, you can know what is the minimum and the maximum. So if you want to generate a frequency, you have to make sure it is within the range so that if you can use it or not. Okay. Now I'm going to talk about the register I talked about here. I told you here we have here a prescale and also we have here a prescale, and there are 2 different prescale. One for clock A and the scale to clock A, also for clock B and scale to clock B. Okay, so where are these scales? It's in a register. This is the name of this register. This is what's the name of this register? Yeah, this is the name of the register here, guys. This is the name of the register. You can see here we have 3 bits. These 3 bits, by whatever you put here, you can select a different prescale. So here the prescale is 1, here is 2, 4, and so on until 128. Same thing here. You can put here whatever you want to, but this is for clock B, this is for clock A. Okay, that's how you can, just one register, you can write some values here. Number 2, I told you for a channel 0, 1, 4, 5, you can select the clock source can be clock A or scale to A. For channel 2 and the 3, 6, 7, it can be clock B or scale to clock B. Okay, how can I do that? Very easy. Programming, very easy. So every channel has only 1 bit, right? If I put 0 in this bit, so it's gonna come from clock A or B. Okay, based on it's a channel. If you put 1, so it's gonna come from scale to clock. Very easy. For example, if you look at channel 0, so I'm here. Channel 0, I'm here. If you put 0, so that means the source of the clock of channel 0 is gonna come from clock A. If you put 1, that means the source of the channel 0 is coming from clock scaled A. Okay. So this is how can you select the source of the clock. This is number 2. Another register. I told you pulse width modulation. Once you set the circuit, CPU doesn't need to do anything. Once you set the circuit, you can just generate a square wave forever. Okay. Someone can ask me, okay, what if I want to turn it off at some point? Can I do it? Or once I generate it, I have no control on the signal? The answer is no. You can turn it on and off if you want. For sure, if you turn it off, so that means it's going to become 0, so no signal. If you turn it on, so you run the signal. Is that okay? So how I can turn on here again? No interrupts. Don't be confused. Okay, I know I talked about interrupts for a while. But now this topic has nothing to do with interrupts. Okay, so now how I can do that? Very easy. So every channel should have only one bit, and this bit here, for example, this channel 0, channel 1, channel 2, and so on. For channel 0, as you see here, guys, if you put in this bit, if you put 0, you actually disable. Disable means there is no signal. You turn the signal off, no signal. If you put 1, you enable. Usually, the signal you are gonna generate a signal. Very easy, right? So it's just one bit. You already know how to set some bits, how to clear some bits. Very easy. Okay. The second thing here also we have in the configuration. That's what we call polarity. Okay, polarity. Polarity means you can generate a signal this way. Okay, this is. Or you can generate this way, whatever you want to do. So we have this one, and I think most of the time we can go for this one. Again, most of the time can go this one. So that's what we have here. So how can we do that? So have two polarities, same thing as you have done before many times. Every channel has one bit. Okay, so one bit is going to select one polarity, which is if you put 1, so you are going to generate this polarity. If you put 0, you are going to select this polarity. Is that okay? So here, if you select this one this way, as I said, from here to here, that's what we call pulse width modulation dotty. This is the name of the register. It's going to control how big is this one. Okay, but if I select this polarity, that means this part is going to be pulse width modulation dotty. Okay, so that means in the very beginning, I'm going to start with the high, but here I'm going to start with the low. Okay, but anyway, I think we can. I really, if you ask me, is there a reason to select this one over this one? I don't think so. So I think if most of the time we can select this unless there is a reason for that. Okay. Another thing here also we have here alignment. So what alignment means? Alignment means we have two types of alignment. We have here what we call left alignment. So like this signal here is left. So here it's alignment to the left. Okay. This is the beginning. This line here is the beginning. Or for sure, this is the polarity. Don't be confused. Polarity is something else. Alignment here. So this is the beginning. Okay. And this is the signal here. So if you have a signal, do you want to start? So for example, if you have a signal like this one, do you want to start from here or you want to start from here? Okay, so this is what we call alignment. Again, if you ask me, I don't see any reason, unless for sure it depends on the application, but maybe if there is no reason, you can all the time go with this alignment all the time. There is no need to do this, okay, unless for sure this reason. So we have two types of alignments. One is called left. Left means I'm going to start with the high or with the low, as you see here. Another one is called center. Center, that means I'm going to start here, as you see, center here. So again, how can you select the alignment? Again, each channel has one bit, right? So here in this bit, if I put 0, so you are asking for left alignment. If you put 1, you are asking for center alignment, okay? So now I'm going to come to how can you program this pulse width modulation, which is very easy. I'm going to tell you how. Okay. Again, I have this formula here. Okay. I have formula. So all what you have to do, guys, I need a certain frequency. Like here, I'm saying I need 100 kilohertz frequency. So this one has to be 100 kilohertz. Okay. So if you look at this equation, it's like an equation. So in this equation here, I have two unknowns. Okay, so if you look at this equation, you can see here, in order to have 100 kilohertz here, so that means prescale times period should equal 240. Okay, I just did multiplication, right? Just math. Okay, 240. So if any value select here, so that the multiplication is 240, it's okay. That means you may have multiple options. For example, I can put in the prescale, I can put 1, and period I can put 240. Is that okay? In prescale I can put 2. One here I have to put 120. Any multiplication, if you can make 240, so that this equation is going to give me 100 kilohertz. Is that okay? But keep in mind, that's what you should understand. Keep in mind, for prescale, we don't have all numbers. For prescale, that's all what we have for prescale: 1, 2, 4, 8, 16, 32. It's 2 to I, by the way. Okay, anyway. And for period, for period, we have numbers from 1, as we see here, from 1 to 256. This is the range. Okay. Same thing here. I'm giving you another example. If you want to generate 50 hertz using the same example, again here, I'm assuming I'm using clock A. That's why I'm using the formula for clock A. If I go back, remember, I give you two formulas here. Well, yeah, here we have two formulas here. Let me. Yeah, we have two formulas here, as you see. One formula for A, one formula for clock scale to clock A. Okay, so number one, you have to decide, I'm going to use this one or that one, and then you have to use its formula. Okay. Yeah, so this is another example. If I make it 50 kilohertz, that means the multiplication, any value, multiplication times the pulse width, it has to be 480. Now, some values may not work here. For example, if I put here 2, if I select here 2, it may not work. Why? Because if you put here 2, sorry, if I put here 1, it's not going to work, because if you select here 1, that means this one has to be 480. It's not going to work because the maximum here has to be 256. Is that okay? Yeah, I forgot to tell you something very important, guys. Pulse period, this period is a byte. As I explained before, any byte should take value from 0 to 255. So how it comes is 256. How it comes? I'm going to tell you how it comes. Again, let me say it again. Pulse width modulation period should be a byte, right? This byte, as I said many times, should take a value from 0 to 255. Is that okay? However, it may, here I said the range can go up to 256. Where 256 come from? From the 0. So here, if you put 0, it's not going to be counted as 0. 0 is not, it's going to be counted as 256. Okay. Here I give you another example for if I use a scale to clock A, just another example. It's just, again, it's just a formula. So, for example, here I want to generate, if you can, for example, if I want to generate 500 hertz, for sure you should not. Here I try to use clock A. You should not even think about it, clock A, because you remember when I explained about the minimum and maximum for clock A. Let me go back. I told you the minimum should be 700, so I cannot generate 500 from clock A. Even if you try to do it, it's not going to work. That's what I did. So I tried to generate 500. It didn't work because I have to find two values here. When I multiply them together, I'm going to get 48,000. It didn't work because if I put here the maximum value, which is 128, that's what I did, and put here the maximum value 256, I found my maximum. I cannot get 48,000. Okay, but anyway, I don't need to waste my time here. The first thing you have to do, once I get a frequency, you have to make sure it has to be in the range. So this one cannot come from here because the minimum frequency is 700, but it can come from scale to clock A, because this one can up to 2 point something hertz, as I explained before. Okay. Yeah, here. Okay. So anyway, so now if I use this one here, so now I have prescale times 2 times this one times this one. This one can take a value from 1 to 256. This one from 1 to 256. Any combination, any numbers here, if you multiply them together, you get this value. I'm going to generate this signal. Very easy. So I can select, for example, 2 for the prescale. For the pre-scale, I can select 2. For the pulse width modulation scale, this scaled A, so I can use this. I can put 60, any numbers, so that the multiplication gives you this number. That means I can generate 5. For sure, there may be multiple solutions, different solutions. But there is something, a trick here, a trick. Okay, look here. When I select, especially for the period, okay, for the period, try to select a number that can make it easy to get the duty cycle you want to get. Remember, the duty cycle, for example, if you make this one, for example, 61, just an example, okay? So if you make it 61, so 61, in order to get 10% duty cycle, it has to be 6.1. The duty cycle register has to be 6.1. For sure, I cannot do it because it cannot be, there is no fraction. It's not allowed to have a fraction. So the best way here, in my opinion, try to select always good number here for the pulse width modulation period, so that you can generate all possible duty cycle you want. And good number here, in my opinion, it can be 100 or it can be 200. 100 or 200. These numbers you can generate any. You can generate any duty cycle, 1%, 2%, 3%, any duty cycle you can generate. Okay. Now I'm going to come to the programming. In the programming wise, all what you have to do, guys, we have just a number of register I mentioned. In this course, all the time I talk about how can you write, how can you set some bit, how can you clear some bit, how can you write data to register. So for C language, for assembly, I'm going to show you now in assembly. For assembly, you have just, as you see here, guys, just the registers. All what you have to move to the register. That's it. Okay. You can do the same thing in C language if you like. So in C language, you can just use the name of the register. You can do that. Or I define here a couple of functions you can use. Whatever you like, whatever you think it's okay. So here I have a function to enable, and you have to tell me which is channel. I have a function to disable. I have a function here to set the duty cycle. So you have to tell me which channel, for example, channel 2, and you have to tell me what is the duty cycle. Anyway, so we have a number of functions here. So now let's have a program here. I'm going to show how it is very trivial to program it, very trivial, because all what you have to write to register. Once you write to register, you generate a signal. That's it, done. So programming wise, it's very trivial. We have done it many times before. Just write to register. Okay, that's what I'm going to do now. Now, I want to generate 100 kilohertz frequency with 50% duty cycle. Okay, the first thing you have to decide, are you going to use clock A or scaled clock A, as I said before. In this example, I'm going to use clock A, for example. Okay, so this number 2, you have to use the formula for clock A, and then it has to be pre-scale times the period should be 240. So I have to select some values here so that the multiplication is 240. And that's what I did here. So here I decided to select 2. Here I decided to select 120. Is that okay? One more thing here. Here, I need the duty cycle should be 50%. That means the duty cycle here has to be 60. Why 60? Because it's because the period is 120, so the duty cycle should be 60 out of the to make 50%. Okay, so now I'm going to come to the programming, which is very easy. So now I have here this clock here where you have to select. So I told you we have one bit to select clock A. This one should help to select clock A. Okay, for sure you can use move, or you can use bit set and bit clear to set one bit. Okay, and so on. Next one here, this is the pre-scale. This is the value for the pre-scale. This is for polarity. Okay. The next one here, this is for alignment. Okay. So I'm gonna make it left alignment. Next one is the period. So I'm gonna write 120 to the period, and then I'm gonna write 60 to the duty cycle. Okay. Next one here, here we have like I told you. Let me go back to explain something here quickly. Yeah, I explain here how it works. The way it works is, if I put here in the period here, if I put 100, that means every 100 cycle from here, I'm going to generate one cycle from here. That's what I said. How it is done in reality, there is a counter. So it has to count. Every 100 here, I count here 100, so I'm going to generate only one here. Okay, so you will see now in the program, just for the first time, I have to clear the count so that the first signal becomes correct. Okay. So here, because maybe the counter has some values. So that's exactly what I did. You see here, guys. So I have to reset the counter so that for the first signal, it has to count for the whole number. For example, here 120, it has to count 120. Otherwise, if the counter has, for example, 20, so that means the signal I'm gonna generate is gonna be for 100 because I already have 20. The problem is gonna be only in the first one because starting from next one it should be okay. But anyway, so just to make from the first signal, first cycle, make it correct, you need to clear it here. The last thing I'm gonna do here is what we call 8-bit mode. I'm gonna explain it later what I mean by 8-bit mode. Okay, so but leave it for now. Okay, so what I wanna do here, guys, once I did that, once I finish, that's it. Once I finish the configuration here, guys, I'm done. If you go measure, if you connect this pin here, which is I think which channel here I used. I think I used the channel 0. Yeah, 0. You can see here. So if you take PP0 and connect it to the scope, you will see this signal. We already generated the signal. So once you do that, we already generated the signal. Okay, I'm done. You don't need to loop. You don't need to do anything. There is no interrupt. You don't need nothing. Just once you do the configuration, the signal is gonna run forever. Now I want to add something here, guys. I'm gonna use a switch on PTH. In one position of the switch, I'm gonna enable the signal and disable the signal. That's what I did here. If you look here, guys. So here, I'm gonna if this one if it is branch if clear, so I'm gonna look at one bit. If it is 0, I'm gonna come to here to bit set, okay, to enable. Okay, otherwise I'm gonna come here to disable. So here you have one switch. This switch should enable or disable the signal. Okay, and you can see here how can you enable or disable a signal. Very easy. You have a register, bit set and bit clear. We work only in one bit. Okay. We have another program here, guys. In this program, and that's very interesting. Now you can see now what I said earlier. How I told you one of the main advantages of pulse width modulation is the duty cycle. You can change the duty cycle easily. Okay, you will see in this program. Okay, so now what I wanna do here, wanna generate a signal, and every time I push a button, okay, I wanna increase the duty cycle. Okay, and when I press another button, I can reduce the duty cycle. Okay, so I have two push buttons. One of them, when I press, I increase. So every time I press, so duty cycle, if it is something like that, when I press, I increase the duty cycle, and so on. The other way is going to decrease the duty cycle. Okay, so let's see how it works. Very easy. First of all, this is the configuration. Once you do the configuration, signal is generated. That's it. So we are done, right? Now, this is the part I'm going to talk about here now. So every time you press this button, I'm going to go to increasing. If you here I'm using two switches, okay, two push buttons. If you press one of them, I'm going to go to increasing. If you press the other one, I'm going to go to decreasing. Is that okay? In increasing, this is the interesting part. Okay, guys. In increasing, okay, here. So here, what I'm going to do here, as you see here, guys. Yeah, what I'm gonna say, pulse width modulation duty 0, okay, and then I'm gonna add 10 and return it back. So what I'm doing here, I'm adding 10 to the duty cycle. So if you have, let me go back here to explain exactly what I'm saying here. For example, if I say this one has to be 100, and this one, for example, I start with 20, I push a button, so I'm gonna make it this one 30 cycles. So I'm going to get it bigger, or I'm going to make it 40 or 50 or 60. You can make it bigger, okay? Or you can make it reduce it. You can make, so that's what I'm saying. It's very trivial to change the duty cycle, very trivial. All what you have to do, you have a register, increase this value to increase the duty cycle, reduce this value to reduce the duty cycle. Very easy, right? So that's exactly what I did here. So here what I did, here I add 10. Every time I press a button, I add 10. Here, every time I press a button, I subtract 10. Okay. This is just very easy here, guys. I'm going to leave it to you. So here I want to generate quickly. I want to generate 4 signals. Okay. These are, I give you all the data for the 4 signals. So it's up to me how you manage it. So for example, I decided, I'm the one who decided, okay, so I'm gonna use but yeah, remember when you select should use clock or scale to clock, you have to remember minimum and maximum. So if you use clock A or clock B, this is your maximum and this is your minimum. If you use scale to A or scale to B, this is the maximum and this is the minimum. Is that okay? So now let's see. So now I decided I'm going to use channel 0 and channel 1 for the first two signals. Okay, channel 0 and the channel 1. Is that okay? And now let's see how it's going to work. And now I decided to use clock A to generate this one. For this one, I'm going to use clock A. So that means this is the equation here. This is the first equation we have, okay? In order to generate 120 kilohertz, I just plug in the formula. So this is the equation, okay? This is number one. Number two, here I'm going to use channel 1. And here I decided to use scale to clock A. And now this is the formula I have here. In order to generate 20 kilohertz, I plug in the equation. This is the second formula I have, okay? So now look here what I did, guys. I have a number of constraints here. This is the first one. This is the second one. That's what I have just explained right now. So I have to select some values here so that the multiplication of these two values give you 200. And the multiplication of these two values, three values should give you 600. Is that okay? Is that everything? No, it's not everything. Yes, there is another important thing here. Now, this one should be 10% to duty cycle. That means when I select this one, I have to make sure it has, when I multiply 0.1 times this one has to be integer, because this is what I'm going to put in the duty cycle, right? Same thing here. This one should be 30%. Same thing. That means if this one 0.3, I'm going to multiply it by pulse width modulation period, okay? I have to make sure the result here is integer. Is that okay? So that, because this is the number, for sure I cannot put fraction in the duty cycle register, okay? So based on this constraint here, again, you need to look for a solution here. So it's just very easy. For example, here, remember prescale is common here. It's just a common part here, okay? So for example, here, you can select one value for prescale. I think I selected here 1 and 1, okay? And then if this one is 1, it can work because this one can be 200, and 200 should be okay because 200 can have 10%, right? 10% of the 200 is 2, right? Oh, sorry, 20, right? Okay. So that's what I can put in the duty cycle. So I'm done with this one, okay? And now let's look at this one here. Here I can, what I did, yeah, I can start with this one. I told you before, try to select here a number that can be multiplied by 0.3 to give you integer. For example, if I select here 100 or 200, here I decide to select 200. So if I put 200 here, that means this one should be 3, right? So that I can get 600 here. And it's still 200, I can get 30% of this one and still integer. Anyway, I have another example here. You can look at this example. It's exactly the same thing. Okay. Now, I have one more program here. It's about how can you make the light dim. And again, the idea is very easy. As I told you before, the idea is that I'm gonna, if this is, okay, let me explain here. If this is a duty cycle, so this is, yeah, here, by this way, I'm gonna get, it's gonna be maximum light or very high brightness. But if I make something like that, okay, so now I'm dim. If as I move this way, I'm gonna make it dim, as you see now. For example, sorry. Yeah, so as I move here, I actually reduce the duty cycle, and as I reduce the duty cycle, I'm gonna make it dim. Okay, and that's exactly what I want to do here. Okay, and again, to reduce it, it's very easy. Just one register, you can reduce it. So, but the way I want to reduce it, I want to reduce it gradually, so that it looks nice. So I'm gonna reduce it gradually. What you mean by gradually? That means in the first second, I want to reduce pulse width, the duty cycle by 1 every 100 milliseconds, and in the next 4 seconds, okay, I'm gonna increase the speed of the reduction. Okay, so I'm gonna dim faster. Okay, so here I'm going to decrement it by 2 every 100 milliseconds. I'm going to show the program. So look here at the C language. Number one here, this is just a configuration, guys, so I'm not going to talk about it. This is similar to what I explained before. It's just a configuration. So once I finish the configuration, I already generated a signal, so I already have a signal. Okay. Now what I'm gonna do now is that's what I told you. Okay, what I told you here, guys. So in the first 1 second, so here I created a for loop for 10 times, 10 times. Okay. So here this is 1 second. Why this is 1 second? Because it's 10 times, and every time I'm gonna make a delay for 100 milliseconds. Okay, so total is gonna take 1 second. Okay, so you can see here for 1 second, every 100 millisecond, I'm gonna reduce the duty cycle by 1. Very easy, very easy. So I'm gonna reduce the duty cycle by 1. Once I'm done with the first second, so here this one should be 4 seconds. 4 seconds. So here that's why I need 40. So here I'm gonna create 40 iterations. Okay, and as you see here, every 100 millisecond, I'm gonna reduce it by 2. Okay, very easy, right? This is assembly. It's nothing new. It's exactly the same thing, but I just use the format of the assembly. Here I reduce 1 time. Here I reduce twice. Okay. Anyway, the last part here in this section and in this chapter, I want to talk about the idea of concatenation. What you mean by concatenation? I'm going to tell you what is the problem, and then I'm going to explain how concatenation can help it. Very easy, right? So I'm going to tell you what is the problem. Let me go back here, guys. Yeah, here. I told you guys here I have pulse width modulation period, and this one should take a value from 1 to 256. This one should take a value from 1 to 256, as I said before. Okay, and then by this value, I can get, this is the range of frequencies. For example, if I put the maximum value, so this is the minimum frequency I can get. Also, this is the minimum frequency I can get, because this one, it's a byte. This byte cannot get more than 256. Okay, it's a byte. Now the question, this is the problem I'm gonna try to solve now. The problem is that, what if you need lower frequency? What should I do? Okay, guys, let me say it again. This is the problem. The problem is that what I explained so far, if this one is a byte, so it has to take a number up to 256. And if I use 256 and use the maximum value for this one, okay, by this way, the minimum frequency I can get this one and this one. Is that okay? So my question now is, what if I need lower frequency? What should I do? Here comes the idea of concatenation. I'm going to explain what I mean by concatenation. But the idea is that, okay, what if I mix this one, instead of making it a byte, this one currently it's a byte, and we have one of this one in each channel. So each channel has a register like this one, and it is a byte. Okay, so if I can make this one a word, so this number can be bigger. Instead of 256, this number can go up 65,536. Can be a bigger number, so that this frequency can be much lower. This is the main idea. So someone can ask me how I can make it a word. It's a byte, hardware byte. Yeah, the idea is that I can take two channels, I can concatenate them together. That means these two channels, I'm gonna use the period of the first channel, I'm gonna use the other period of the second channel. This is the main idea. So here our pulse width modulation period is gonna be two bytes. 2 bytes. One here is coming from one channel, the other one is coming from another channel. This is the main idea. That's what we call concatenation. That's why here, what I'm saying, we have now 2 modes of operation. We have 8-bit mode of operation, and that's what I just explained right now. And now that's what I'm going to explain now. We have what we call 16-bit mode of operation. In case of 16-bit mode operation, as I told you, I can get 2 channels. For example, I can get a channel 6 and the channel 7 together, and I can concatenate them together to generate only 1 signal. Okay, but for sure this signal can be much lower. Same thing I can do for channel 4 and channel 5. Okay, and also a channel 2 and the channel 3, a channel 0 and 1 together. So here instead of having 8, now I can have only 4. If you concatenate all of them, you don't need to concatenate all of them. You can only, for example, so now you have the option. So now, for example, you can concatenate this one. But for example, for channel 0, 3, and 4, I can use them individually, or I can use them what we call 8-bit mode. When I concatenate, I say it is 16-bit mode. So now I'm going to explain, okay, quickly. This is the last part. How can you concatenate? Very easy, very trivial. Look here, guys. Here in this register, this is the name of this register here, guys. In this register, every 2 channel has 1 bit. So this one for channel 0 and channel 1. This one for channel 2 and 3. This one for channel 4 and 5. This for channel 6 and 7. Okay. If I put 0, that means they should work in 8-bit mode, separate. So they are separate. Okay. If you put 0. If you put 1, no, I concatenate. Very easy, right? So here you can put 1 or 0. 0 means separate, so 2 separate channels. If you put 1 means it's concatenate. So it's going to be only 1 pin or 1 signal you can generate. Okay. So now someone can ask me, okay, if you concatenate, for example, if I concatenate here, guys, a channel 0 and 1. Okay. So concatenate means now I should have only 1 channel. It became 1 channel. Yeah. When it became 1 channel, okay, now the question is that now I need enable bit, right? I need the other configuration. So now I have 2 enable bit also for it, because I have 2 channel. So for every configuration I did before, I had 2 channels, right? So which one now after concatenation, which one I have to use? The answer is that as it's written here, guys. So here you have J and K. This is J and K, right? K is the bigger one. So actually you have to use the bigger ones. Let me read it here. So if you concatenate, that means becomes, and that means if you want to use, so the K output pin, now, because now you have 2 pins, 0 and 1. Which pin is going to generate the signal? K, the one at K, okay? Also, so here you have to use, here's the same thing, the one at 3, bigger one, the one at 7, okay? And also, for example, which clock selection, okay? So now for clock selection, I have for the 2 channel, I'm going to use the bigger one. Is that okay? Anyway, so now I just want to show you how this can be useful, as I told you, okay? For example, if I use clock A, guys, and in 8-bit mode, I told you this is my maximum. I'm going to put here 256, and this is my minimum frequency should be this one. Okay, now if I concatenate and I make it 16-bit, okay, so now this one can go up to 65,536. I can put it here. So this can reduce the frequency, minimum frequency, up to 2.8 and so on. Okay, and this is the main advantage here, or this is the justification or the reason why you wanna why you want to use concatenation. Okay, so let me summarize what I said here, guys. In concatenation, you have 2 channels, 2 pins, okay, and every channel should have its own configuration bits, configuration register, as I explained before. So we have to use, for configuration, we have to use always a bigger number. Okay, for example, here I concatenate 0 and 1, so that means the enable should be at 1. So that means the signal should be generated at pin number 1. Okay, that means if you want to select a clock, it has to be from 1 and so on. Okay, but for the period, what I did, I'm gonna concatenate the pulse width modulation period 0 and 1. This one is 1 byte and this is a byte. Okay, and all what you have to do, you have to write a word to this one, and this word is gonna written on both of them. Same thing for the duty cycle. Okay, for the duty cycle, you have to write a word to this one, and this word is gonna written on both of them. Okay, so this is just an example to show how it works. So here I want to use a channel 0 here. Yeah, I want to use channel 0 and 1 concatenated together. Number 1, the output is gonna come from channel 0, from number 1, as I said. Okay. Number 2, if you want to set the clock, you have to set the clock of 1. If polarity, it has to be polarity of 1, because okay. Clock selection, you have to program 1, not 0. Okay. So now, yeah, this is a concatenation. For concatenation, you have to put, let me come here, you have to put 1 here. Okay, that's what you have to do here. You have to put 1 here. Also, alignment. So for alignment, I'm going to use the bit of 1. Okay. Now for period, I'm going to use, I'm going to write to this one, but actually I'm going to write a word to this one, but the way it's going to be done is going to be this one and next one. Okay. So here I'm going to write 30,000 to this one. So it's going to be written on this one, next one. Here 24,000 on this one. So it's going to be this one and next one here, because now this is the main objective. Now I have, instead of have byte duty cycle, byte period, I'm going to have a word. Okay. And then this is the enable. In the enable again, I'm going to use this enable for number 1. Okay. And I am done with this chapter. Okay. Thanks, Gaspar.